In this video, we are going to talk about the development of Lewis structures for molecular compounds or covalent molecules. We're going to start with the Lewis structures of simple covalent molecules using the electron dot symbols as our guide. And then we're going to move to a more complex version of the development of Lewis structures, which works better for all Lewis structures of molecular compounds. So let's get started in Lewis structures of simple covalent compounds. The simple covalent compound Lewis structures can be developed from the electron dot structure of the element. Just like we use the electron dot structure of the element to develop ionic compounds, we can use that electron dot symbol of the element in order to determine the covalent molecule's Lewis structure. The valence electrons will be shared until a duet for hydrogen or an octet for all other elements is achieved. Again, this is about the valence electrons of an atom of an element. So let's just look at some. Let's look at hydrogen. Hydrogen in nature is always found in a pair. The hydrogen atom, being in group 1, has one valence electron. The two hydrogens each have a valence electron, which we represent as an electron dot. Now, because hydrogen is a non-metal, we know that the electrons are shared between the two atoms. And so the hydrogen on the left is going to donate its electron, and the hydrogen on the right is going to donate its electron. So that ultimately the two hydrogens are sharing their electrons. Now, the hydrogen on the left views itself as having a pair of electrons called a duet. The hydrogen on the right also views itself as having a pair of electrons or a duet. So hydrogen, by sharing a pair of electrons, thinks that it has a duet, which is what hydrogen wants. Now, those two electrons are frequently represented as a line. So a line represents two electrons, and we frequently will represent hydrogen as H bond H. Now let's look at another example. Let's look at oxygen. Oxygen also, when it is found in nature by itself, comes in pairs. The oxygen has 6 valence electrons, and that is true for both of our oxygen atoms. Let me start that again. Now, our oxygen atom is going to share a pair of electrons. And when it shares one pair of electrons, the structure that emerges is this structure. When we count up the number of valence electrons, the atom on the left views itself now as having 7 valence electrons. The atom on the right also views itself as having 7 valence electrons. We have not achieved the octet that all other atoms except hydrogen is going to obtain. So oxygen is going to share another pair of electrons. When oxygen shares another pair of electrons, this structure emerges. Now the oxygen on the left views itself as having all of the electrons that are found in the bond plus its two pairs of electrons. And it views itself as having 8 valence electrons. The oxygen on the right also sees itself as having 8 valence electrons. In other words, each of these have an octet. Keeping in mind that a pair of electrons is represented with a line, we typically will see oxygen written with both pairs of electrons represented as a line, and that is going to be referred to as a double bond. So this is the Lewis structure for an oxygen molecule. Let's look at another example. Let's look at nitrogen. Nitrogen also, when found in nature, comes in pairs. Nitrogen, being in group 15, has 5 valence electrons. When we share one pair of valence electrons between the two atomic nuclei, the structure that emerges is this structure. The nitrogen on the left views itself as having 6 valence electrons. 2 within the bond and 4 that it owns on its own. The oxygen on the right also views itself as having 6 valence electrons, 2 within the bond and 4 on its own. We have not achieved an octet, so this is not the structure for nitrogen because, again, the only atom that does not get an octet is hydrogen. Hydrogen needs a duet, but all other elements must have an octet. That being said, the nitrogen is going to share another pair of electrons between the two atomic nuclei. And what emerges is this structure. Now, the nitrogen on the left views itself as having 7 valence electrons. There are 4 that are shared between the two nitrogens and 3 that is owned by the nitrogen by itself. The nitrogen on the right also views itself as having 7 valence electrons. 4 that are shared between the two atoms and 3 that are owned by itself. Again, we have not achieved an octet. So the nitrogen is going to share another pair of electrons between the two atomic nuclei. When it does so, this structure arises. Now, when the nitrogen on the left views its world, it sees, okay, I'm sharing 6 electrons, that's 6, plus 2 that I own, so that gives me an octet. The nitrogen on the right views itself as having 6 that are shared and 2 on its own, so that gives it an octet. So our nitrogen achieves an octet when it shares 6 valence electrons between the two atomic nuclei. Again, each pair of electrons is represented with a line. So to represent 6 electrons, 3 pairs, we develop 3 lines. And that is what you'll typically see with the development of nitrogen. Now, I want to bring up a couple of pieces of information. First of all, I want to bring up these bond types. We had a single bond, which was represented with a single line. It occurs through the sharing of 2 electrons. Our hydrogen was an example. We have a double bond, which is going to be represented with 2 lines. It's the sharing of 4 electrons. Each line represents 2 of those electrons, so 2 lines represents a total of 4 electrons. The atom that or the molecule that we looked at that had this was our oxygen molecule. It had 4 electrons shared between the 2 atomic nuclei. A triple bond is the sharing of 6 electrons. Since we're sharing 6 electrons, 2 electrons represent a line, so therefore a triple bond was represented with 3 lines. The example that I gave was that of nitrogen. Nitrogen has 3 bonds between the 2 atomic nuclei. So we call these bonds by the type of bond they are, which is single bond, double bond, and triple bond. And we understand that each line in those bonds represents a pair of electrons. Another thing I wanted to bring up is I brought up the fact that hydrogen in nature comes in pairs, oxygen in nature comes in pairs, and nitrogen in nature comes in pairs. There are actually 7 elements that when found in nature, you're always going to find in pairs, and these are referred to as the diatomic elements. Now, you can memorize these diatomic elements a couple of different ways. The first way you can remember is there are 7 of them, and it forms a nice 7 on the right-hand side of the periodic table, and then you add hydrogen to that list. The second way you can memorize these diatomics is through the term Brinkelhoff. Brinkelhoff tells us which elements come in pairs: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These are elements that are always found in pairs when they are found in nature all by themselves. Again, this is when they are all by themselves. It is different once they form a compound. But when they're just all by themselves, they will come in pairs. And to name these diatomic molecules, we simply give the name. So in other words, Br2 is bromine. H2 is hydrogen. We give the elemental name for these. So O2 is oxygen. And so on and so forth. Now we can continue using the electron dot symbols of the elements for other simple molecules like water. When you have something like water, hydrogen is going to be a terminal atom. Hydrogen will always be a terminal atom. And so we can draw out our structure with 1 hydrogen, an oxygen, and a second hydrogen. Now, we're going to do the same thing as we did before. The hydrogen is going to share its electron with the oxygen to make a single bond between the hydrogen and the oxygen. The other oxygen is going to share a pair of electrons between the oxygen and the hydrogen in order to create a single bond. Now, the hydrogen on the left views itself as having two valence electrons, so it has a duet of electrons, which means hydrogen is happy. The hydrogen on the right also views itself as having two valence electrons, called a duet. Whereas the oxygen views itself as having 4 electrons in lone pairs and 4 electrons in bonds, so that it has 8 valence electrons, called an octet. So the structure that we typically draw for oxygen is going to, for water, excuse me, is that the water is going to have 2 hydrogens with a single bond to an oxygen atom, and the oxygen atom is going to have 4 dots still remaining on it. Now, these bonds and dots are referred to as a certain type of group. A bond, whether it is a single bond, a double bond, or a triple bond, is called a bonding group. Now, when an atom has electrons owned strictly by that atom, they are called a lone pair. Sometimes referred to as a non-bonding group. So in other words, hydrogen has 2 bonds, 2 bonding groups, and the oxygen has 2 lone pairs. So bonding pairs are electrons that are shared by 2 atomic nuclei, whereas lone pairs are electrons that belong solely to a single element. Again, with water, the hydrogen-oxygen bond would be a bonding pair because those electrons are shared between the hydrogen and the oxygen. Whereas the dots that still remained on the oxygen atom would be lone pairs, because the oxygen owns those electrons all by itself. We can continue this with carbon dioxide, and we'll introduce another couple of terms. So carbon dioxide, one thing you need to know is that carbon is always going to be the central atom. Therefore, the other elements will be the terminal atoms. So the structure for carbon dioxide is going to put carbon in the center and oxygen around it. Now, carbon has 4 valence electrons. Oxygen has 6 valence electrons. We know that carbon has 4 valence electrons because it's in group 14. The last digit is a 4. So therefore it had 4 valence electrons. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons. Now, to make carbon dioxide, the first thing we're going to do is we're going to share a pair of electrons between the terminal oxygen and the central carbon. And we can do this for both of our oxygens. So we can create this bond. And when we do so, the oxygen still has a lone pair, and the carbon still has a lone, the oxygen has 2 lone pairs, and it still has a single electron that is not paired. The carbon has 2 electrons that are not paired, and the oxygen on the right also has an electron that is unpaired. If we count up the number of electrons right now, this oxygen on the left will view itself as having 7 valence electrons. The oxygen on the right also views itself as having 7 valence electrons, and our carbon views itself as having 6 valence electrons. So in other words, this molecule is not happy because nobody has an octet, and all of these atoms must have an octet. All atoms other than hydrogen must have an octet. Now, what happens is the oxygen is going to share another pair of electrons with the carbon. And this is going to be true for each of our oxygens. We're going to share another pair of electrons between the two, so that the structure that evolves is this structure. Now, if the oxygen on the left views its electrons, it has a double bond, which means there are 4 electrons, and there are 4 electrons in lone pairs, so this views itself as having an octet. The oxygen on the right also views itself as having 8 valence electrons, 4 electrons in the double bond, and 2 lone pairs. Therefore, it also has an octet. And our carbon sees itself as having 2 double bonds, each with 4 electrons. Therefore, it has 8 valence electrons, which is an octet. So the Lewis dot structure for carbon dioxide has carbon double bonded to each oxygen in the molecule. One thing I'll point out is, again, carbon is always going to be the central atom. It is always going to be the center of attention. Second thing I'll point out is carbon always has 4 bonds. Always. And third thing I'll point out is that chemistry loves some symmetry. So when I put a double bond on the left, and it was insufficient in order to give the carbon an octet, I had to put a double bond on the right, so that there was a double bond on the left and a double bond on the right in order to make this symmetrical. So carbon is always the center of attention. Hydrogen will always be an external atom, and chemistry likes symmetry. So what this particular portion of the video has illustrated is that for simple organic molecules, you can use the electron dot symbol of the atom. And when you start sharing electrons, The number of electrons shared between two atomic nuclei is going to be dependent upon the number required in order for each element to achieve an octet, except hydrogen, which needs a duet. When you're making these structures, you're going to potentially encounter single bonds, double bonds, and triple bonds. These are bonding groups. But you also may encounter lone pairs. The lone pairs can exist on an external or terminal atom, and they can exist on a central atom in order to make the octet. But the driving force behind it is making the octet. Carbon will always be in the center. Hydrogen will always be a terminal atom. And chemistry likes symmetry. When you make a double bond on the left, there's a chance that you're going to make a double bond on the right in order to create this nice, beautiful symmetry among the molecule. Now, the electron dot symbols are very useful in developing Lewis structures. But when you get to more complex Lewis structures, the electron dot symbol is going to be cumbersome to use. It's going to be, it's going to potentially give you an incorrect structure. So what we're going to do next is we're going to talk about how to develop Lewis structures using a set of steps that will be useful for all molecular compounds and not just the simple molecular compounds. So step number 1 starts with calculating the total number of valence electrons that is going to go into your Lewis structure. Now, if you have an ion, you do have to take into account the charge on that ion when determining the number of valence electrons that will need to be distributed throughout the molecule. If you have an anion, you're going to add the indicated number of electrons to the total. Basically, the reason for this is because if you have an anion, it's saying you have excess electrons. So you got to add that excess of electrons to the total number of electrons. For a cation, we're going to subtract the indicated number of electrons from the total. That's because if you have a cation, it means you have more protons than you do electrons. Therefore, you've lost some of those electrons. So step number 1 is to calculate the total number of electrons. And when we're talking about the total number of electrons, we're talking about the total valence electrons for the Lewis structure. Second thing is we're going to write the correct skeletal structure for the molecule. This is where things like hydrogen must always be a terminal atom. Carbon must always be a central atom. That's where some of this comes into play. When we're writing the skeletal structure for the molecule, what we're going to observe is that besides hydrogen, the more electronegative atoms are going to be in your terminal positions. The electronegativity can be shown in a periodic table, and you'll receive this periodic table of electronegativity on an exam. I'm not asking you to memorize these electronegativities. Now, I will point out one key factor, and that is your fluorine is the most electronegative atom on the entire periodic table. And francium is the least electronegative atom on the entire periodic table. So negativity decreases, electronegativity decreases down a group, it decreases across a period. And what you may note if you're thinking about your previous atomic trends is for the most part, the smaller the atom, the higher the electronegativity. But again, you're going to receive this periodic table on the test, so you don't have to memorize this. So again, when we're writing the correct skeletal structure for the molecules, the hydrogen atoms will always be terminal, and carbon will always be the central atom. And then if you have other structures, you'll place the more electronegative atom in terminal positions. Just a note here. The note is that you'll observe that the first atom or the first element in a formula tends to be the central atom. This is true except for hydrogen. So when I developed the Lewis structure for water, I skipped over hydrogen and it became oxygen. Oxygen was the first element besides hydrogen in the formula. For carbon dioxide, carbon was the first element in the formula, and it also was the central atom. We're going to notice this for many, many more atoms, that the first element listed in a formula, unless it's hydrogen, is going to be the central atom. Now, when hydrogen is listed first in a formula, you go to the second one in line typically. Okay, so we have counted up our number of valence electrons. We have developed the skeletal structure for our molecule. Step number 3 says to distribute the valence electrons. What we're going to do is we're going to start by drawing a single bond between the terminal atoms and the central atom. In so doing, we're going to do this to give our terminal atoms an octet, except for hydrogen, which gets a duet. If valence electrons remain, we're then going to place them on the central atom in pairs. This is going to be true for most molecules. However, there is something called a free radical. And a free radical has an electron that is not paired up. Free radicals are highly reactive molecules. So that's something to keep in mind. So again, we're going to start by distributing our valence electrons. We're going to draw a single bond between the terminal atoms and the central atom. We're then going to give our terminal atoms an octet by adding dots to the structure. The exception will be hydrogen, which is only going to have a duet. Where then, if valence electrons still remain, they're going to go on the central atom in pairs. Or in other words, you're developing lone pairs for those electrons. Now, how many bonds can you expect an element to have? Well, you'll notice that if for hydrogen it's 1, for period 2 elements, there is only one option. For boron, it's typically 3. For carbon, carbon will always, always, always have 4 bonds. Nitrogen will typically have 3. Oxygen will typically have 2. And fluorine will always have just a single bond. It's when you get to period 3, 4, 5, 6, and 7 that we start to see, well, while for a sulfur atom, 2 bonds may be the correct number, we also can have up to 6 bonds for that sulfur atom if it means that the molecules' formal charges are reduced, which I'll talk about that more here in a minute. So you do see molecules with more than 4 bonds, with more than an octet when you get to the third shell. Now, the reason is when we get to period 3, that means that N is equal to 3, which means that your L values can be 0, 1, and 2, meaning you can have an S, P, and D subshell. Now, just because we don't fill the D doesn't mean it's not there. So the reason you can have what's referred to as an expanded octet when you get to period 3 is because when you get to period 3, that D subshell comes available. Now, some checks. Once you've distributed your electrons around the structure, you're going to check that all elements have an octet. If an element does not have an octet, then that's when you're going to make a multiple bond by sharing a pair of electrons between the terminal atom and the central atom. Again, if you look at the periodic table prior to this, you will note that period 3 through 7 elements can have an expanded octet due to the availability of that D subshell. So we're going to have to figure out how to determine whether period 3 through 7 central atoms need an expanded octet. But before we do that, let's talk about the second check. The second check is, does the Lewis structure represent an ion? Just like when we were developing the Lewis structure of ionic compounds, if you were working on the Lewis structure of a polyatomic ion, for example, that it's still an ion. Therefore, the Lewis structure is still going to have that ion in brackets with the charge as a superscript to the right. The next check that you need to do is to determine if resonance structures are necessary. Resonance structures are 2 or more Lewis structures that have the same skeletal formula, but different electron arrangements. You'll know that you need to draw a resonance structure if more than one valid Lewis structure can be drawn for a molecule without changing the position of the atoms, but only the placement of the electrons. Essentially, what this boils down to is, did you make a conscientious decision about which terminal atom would create a multiple bond with the central atom? But you could have made an equal decision with a different central atom. Finally, We're going to check to see if we need that expanded octet. And the way we're going to check to see if we need an expanded octet is we're going to determine the formal charge on each atom within the molecule. If one resonance structure is more, and the formal charge will tell you if one resonance structure is more likely than another resonance structure to be the correct structure. It tells you if you need to create additional multiple bonds in order to minimize formal charge. So let's talk about formal charge. The formal charge of an atom is going to be the number of valence electrons for that atom minus the number of non-bonding electrons, meaning the dots, on the atom, plus 1/2 the number of bonding electrons on the atom, meaning 1/2 of the electrons that make up lines. Now, we're going to know if our formal charge is, if we need to make an expanded octet, or we're going to know which Lewis structure is better when the sum of all the formal charges in a neutral molecule equals 0, when the sum of all formal charges in an ion equal the charge on the ion, when you get the formal charges as close to 0 as possible for all atoms in the molecule. Now, there are going to be times where formal charge cannot be avoided. And you're going to want, if you've got a negative formal charge, that negative formal charge must be on the more electronegative atom. And then finally, we'll know if we're correct because we won't have like formal charges on adjacent atoms. Okay, to see this in action, we are simply going to do a ton of molecules. We're going to start with the molecules that we did using the electron dot symbols, and we're going to follow these Lewis structure rules instead. So water has 2 hydrogens and it has 1 oxygen. Hydrogen's in group 1, so it has 1 valence electron for a total of 2 valence electrons contributed by our hydrogen atoms. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons contributed by the oxygen, for a total of 8 valence electrons that need to be distributed around the molecule. Step number 2 says to develop the skeletal structure. The skeletal structure will typically have the first element in the formula listed as the central atom, unless that element is hydrogen, and hydrogen must always be the external atom. So in this particular case, it's going to be hydrogen, oxygen, hydrogen. The next step says to give your is to draw a single bond between the terminal atom and the central atom. And we're going to subtract out the number of electrons that are found in those bonds. So each line represents 2 electrons. We drew 2 lines. So 2 times 2 is 4. So we'll subtract out 4 due to our bonds, leaving us 4 valence electrons still to distribute. The next step says to give your external atoms an octet. Well, for hydrogen, it only needs a duet, and both hydrogens right now have 2 valence electrons within that bond, so each hydrogen has its duet. So we can't give hydrogen any more electrons. So the next thing says that if electrons still remain, they go on the central atom in pairs. So we're going to place those electrons on the oxygen in pairs. We subtract out the electrons and we hit 0. Now, when you hit 0, folks, you cannot add any more dots. And the only way to change the number of bonds between two atomic nuclei is by bringing in a pair of electrons from the external atom and sharing it with the central atom. When you hit 0, you cannot add any more bonds. All you can do is bring in a pair of electrons from an external atom and share those with the internal or the central atom in the molecule. Now that we have distributed all of our electrons and we have hit 0, we're going to check, does everybody have an octet? Your hydrogens have a duet because they have 2 valence electrons. Your oxygen has 8 valence electrons, so it does have an octet. It has 4 electrons that are in the lone pairs, and it has 4 electrons in the 2 bonds. So it has an octet. So again, the Lewis structure for water has oxygen singly bonded to 2 hydrogens, and on that oxygen are 2 lone pairs. We can do the same thing for carbon dioxide. We have 1 carbon and 2 oxygens. Carbon is in group 14, the last digit is a 4, so it has 4 valence electrons. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons. The carbon therefore contributes 4 valence electrons, and the oxygens contribute 12 valence electrons for a total of 16 valence electrons that must be distributed throughout our molecule. The next thing is to develop the skeletal structure. Typically, the first element listed in a formula is going to be the central atom. The only exception to that is hydrogens. Since carbon is listed first in this formula, that means carbon is going to be our central atom, and the oxygens will be terminal atoms. The next step says to draw a single bond between the terminal atoms and the central atom. When we draw those 2 bonds, each bond contains 2 electrons. So 2 bonds times 2 electrons means that we have used up 4 electrons within our bonds, giving us 12 valence electrons still to distribute. The next step says to give your external atoms an octet. Well, oxygen currently has 2 within the bond, so in order for our oxygen to have an octet, it needs 6 more electrons. This is true for both oxygens. Each oxygen has 2 electrons within the bond, therefore you have to give it 6 additional electrons in order to make oxygen have an octet. In order to give these 2 oxygens an octet, we used all 12 valence electrons on our outer atoms. And we have hit 0. When you hit 0, all you can do is manipulate what is there. You cannot create more bonds or lone pairs because you don't have any more valence electrons. So therefore, all you can do is manipulate what's there. So I have 8 valence electrons with our oxygens, but I've only got 4 valence electrons currently with carbon. So because carbon does not have an octet, we have to do something with this molecule. So what we're going to do is we're going to bring in a pair of electrons from one of the oxygen atoms. And when we do so, the structure that arises is this structure. Now, the oxygen on the left still has 8 valence electrons. We know that because we didn't alter it in any shape, form, or fashion. The oxygen on the right still has 8 valence electrons. Even though we altered it, what we did is we shared another pair of electrons. So that oxygen views that double bond, which has 4 electrons, as being owned by the oxygen atom. So there's 4 electrons in the bonds, and there are 4 electrons in the lone pairs to give that right-hand oxygen an octet. Now, by sharing a pair of electrons between the right-hand oxygen and the carbon, we've also altered the carbon. The carbon now has 6 valence electrons. It has 2 electrons within the single bond, and it has 4 electrons within the double bond. Because not every atom has an octet, we are not done, because at minimum, every element must have an octet except for hydrogen, which only needs 2. Therefore, we are going to have to share another pair of electrons. And this is where keeping in mind that chemistry-like symmetry comes into play. So we're going to share another pair of electrons between the carbon and the opposite oxygen, and what results is this structure. Because we didn't do anything to the oxygen on the right, it still has 8 valence electrons. The oxygen on the left also has 8 valence electrons. It has 4 found within that double bond, and it has 2 lone pairs that make up the other 4 to give that oxygen a total of 8. Our carbon also now has an octet because it has 8 valence electrons that are found within those 2 double bonds that it has a share of. So this is the Lewis dot structure for carbon dioxide. Now, we can prove that chemistry-like symmetry. Let's say, just for example, let's say that we came up with this structure instead. Why is this structure bad? Well, the answer to this comes in valence electrons. We can do so let's do the valence electrons for our single bonded oxygen. It is the total number of valence electrons. I'm sorry, not the valence electrons. I meant the formal charge. Let's do the formal charge for each of these atoms. The formal charge for our single bonded oxygen is going to be the number of valence electrons minus 1 for every electron in the lone pair, so that's 6, plus 1 for every bond. It's actually a half times the number of electrons in bonds, which there are 2 electrons in bonds, so half that is 1. The other way to say this is it's the number of electrons in lone pairs plus the number of bonds. In other words, that oxygen currently has a formal charge of a -1. Now for our carbon atom, the formal charge on our carbon is going to be the number of valence electrons, which is 4, minus 1 for every dot. Well, it has no dots, plus 1 for every bond. It has 4 bonds. So this currently has a formal charge equal to 0. Now let's do our triple bonded oxygen. Oxygen has 6 valence electrons minus 1 for every dot. It has 2 dots, plus 1 for every bond. It has 3 bonds, meaning that this oxygen has a formal charge of a +1. That means that the total formal charge on that molecule is a 2. Now, we can do the same thing for our actual structure. And when you do that for your actual structure, you have a formal charge of 0 for each of the double bonded oxygens. And you have a formal charge of 0 for our carbon. Therefore, the overall formal charge is equal to 0. So this is definitely the structure that we would report because number one, it meets the octet rule, and number two, the formal charges have been minimized and are as close to 0 as possible. So this structure will not exist because it has a high formal charge. Now let's look at other molecules, some that we haven't done. So let's do HCN. You have one hydrogen, you have one carbon, you have one nitrogen. Hydrogen's in group 1, it has 1 valence electron. Carbon's in group 4, it has 4 valence electrons. And nitrogen is in group 5 with 5 valence electrons. The hydrogen therefore contributes 1, the carbon 4, and the nitrogen 5, for a total of 10 valence electrons that will need to be distributed throughout our molecule. Step number 2 says to develop the skeletal structure. You can look at the formula here and 3 things pop out at me. Number 1, hydrogen always is an external atom. Therefore, it cannot be the central atom. Secondly, carbon is always the central atom. It's always the center of attention. And thirdly, you can use the statement that I gave where you're going to start with the first element in the formula, unless that's hydrogen, and then you move to the second element. So with all this in mind, carbon is going to be our central atom. We are then to place a single bond between our terminal atoms and our central atom. We place 2 bonds. Each of those bonds represents 2 electrons. So 2 times 2 is 4. We've distributed 4 electrons in our bonds. That gives us 6 electrons still to remaining. The next step says to give your external atoms or terminal atoms an octet. Well, hydrogen currently has 2 so it's valence electrons, so it has its duet that it wants. Nitrogen, therefore, is where we're going to have to place these valence electrons. So nitrogen currently has 2 electrons in the bond. In order for nitrogen to have an octet, it needs 6 more electrons. So minus 6 equals 0. When you hit 0, all you can do is manipulate what's there. So we ask ourselves, does everybody have an octet? Our hydrogen has an octet. Our nitrogen, we ensured had an octet because we gave it those 6 valence electrons in order to create that octet. So it has 6 lone pair electrons and it has 2 electrons in the bond for an octet. But our carbon currently only has 4 valence electrons. So our carbon does not have an octet, and therefore this is not the structure for hydrogen cyanide. So the next thing says to bring in a pair of electrons from an outer atom to share with the central atom. So when we do so, this structure emerges. Your hydrogen still has 2 valence electrons, so it still has a duet. It is content. We know this because we didn't alter the hydrogen in any manner going from our first structure to our second structure. Sorry. The Okay, so hydrogen has a duet. Now, if we look at our nitrogen has an octet still, um, because it has 4 in the lone pairs and it has 4 in the double bond. So it has its octet. But carbon currently only has 6 valence electrons. It has 2 within the single bond to the hydrogen, and it has 4 within the double bond to the nitrogen, making a total of 6. Carbon still does not have an octet, and therefore this structure is not complete because every atom must have a minimum of an octet except for hydrogen, which has to have a duet. Therefore, we're going to bring in another pair of electrons from our nitrogen to share with our carbon. And when we do so, this structure emerges. When you have this structure, you have hydrogen still having its 2 valence electrons or its duet. You altered the nitrogen, but nitrogen still has 8 valence electrons. It has 6 electrons in the bonds between the carbon and the nitrogen, and it has 2 in the lone pair for a total of 8, so it has an octet. The carbon atom also has 8 valence electrons. It has 6 within the triple bond, and it has 2 within the single bond, so now it has an octet. This is the structure for hydrogen cyanide. Let's look at another molecule. Look at CH2O. We have 1 carbon, 2 hydrogens, and 1 oxygen. Carbon is in group 14. The last digit is 4, so it has 4 valence electrons. Hydrogen is in group 1. The last digit is 1, so it has 1 valence electron. And oxygen is in group 16. The last digit is 6, so it has 6 valence electrons. The carbon therefore contributes 4, the 2 hydrogens contribute 2, and the oxygen contributes 6, for a total of 12 valence electrons to distribute. The first element listed is typically going to be your central atom around which you're going to place all other elements. You're then going to draw a single bond between the terminal atoms and the central atom. We drew 3 bonds. Each bond has 2 electrons, so that is a total of 6 electrons in the bonds. And we still have 6 electrons still to distribute. The next step says to make sure your external atoms have an octet. Our hydrogen has its version of an octet. It has a duet, which is all that the hydrogen needs. But the oxygen currently only has 2 electrons. So we're going to give the oxygen an octet by adding 6 additional electrons to it. Now that oxygen atom also has an octet. And we have hit 0. When we hit 0, all we can do is manipulate what is present if needed. So how do we know whether we need to manipulate what is present? We see, does everybody have an octet? Again, your hydrogens have 2 valence electrons. They have a duet. They are content. Your oxygen has 6 valence electrons within the lone pairs and 2 valence electrons within the single bond. So it has 8 valence electrons, so it does have its octet. But your carbon atom currently only has 6 valence electrons, 2 within each bond. So carbon is not content. So we're going to have to share a pair of electrons between the oxygen and the carbon. And when we do so, we create a double bond between oxygen and carbon, and then that carbon is also singly bound to 2 hydrogens. When you alter the structure, you see, does everybody have an octet? Your hydrogens do have an octet because they need only a duet. Your carbon currently has 8 valence electrons, so it has an octet. It has 4 within the double bond, and it has 2 within each of the single bonds for a total of 8. And your oxygen also has an octet because it has 4 within the double bond and 4 in the lone pair. So this is the structure for formaldehyde. Okay, I want to take a moment before we continue doing more and more molecules. I want you to think about how each molecule, I want you to think about the number of bonds each atom has in these molecules. In this molecule, the hydrogen had 1 bond, the oxygen had 2 bonds, the carbon had 4 bonds. In this molecule, the carbon had 4 bonds, the hydrogen had 1 bond, the nitrogen had 3 bonds. In this molecule, the carbon had 4 bonds, the oxygen had 2 bonds. Why I wanted you to pay attention to that is if we go back to the number of ideal, you will notice that hydrogen always got 1 bond, carbon always got 4 bonds, nitrogen always got 3 bonds, and oxygen always had 2 bonds. In other words, we could have predicted these structures and the way these electrons have been shared in large part based off of the number of bonds that these atoms prefer. These molecules prefer. So let's look at another example. Let's look at CH2F2. We have 1 carbon, we have 2 hydrogens, we have 2 fluorines. Carbon is in group 14, the last digit is a 4, so it has 4 valence electrons. Hydrogen is in group 1, the last digit of 1, so it has 1 valence electron. Fluorine is in group 17, the last digit is 7, so it has 7 valence electrons. The carbon contributes 4, the hydrogens 2, and the fluorines total of 14. So we have 14, 18, 19, 20 valence electrons to distribute throughout this molecule. The next step is to develop the skeletal structure. We know that carbon is going to be the central atom around which we're going to place all other elements. So we're going to place our carbon with our 2 fluorine atoms on either side. The next step is to draw a single bond between the terminal atom and the central atom, and we're going to subtract out 2 electrons for each bond we drew. We drew 4 bonds. 4 times 2 is 8, so we'll subtract out 8 valence electrons due to our bonds. This gives 12 valence electrons still to go. Our next step says to give our external atoms an octet. So our hydrogens already have their version, which is a duet, because they have a share of 2 valence electrons. And that is true for both of our hydrogens. So our hydrogens don't need any additional electrons. But fluorine does, because fluorine needs an octet. Currently, each fluorine atom only has 2 electrons that are found within the bond between the carbon and the fluorine. In order for fluorine to have an octet, we're going to have to distribute 6 additional electrons to the fluorine in order to give it its 8 valence electrons, which is an octet. We do so for both fluorines, and in giving our fluorines their octet, we used up all 12 of the remaining electrons. So we have no electrons remaining. At this point, you will notice that every time I did this, I said, okay, does everybody have an octet? Well, we know our hydrogens have a duet, which is what they need, and our fluorines have an octet because we specifically distributed some of those valence electrons to the fluorine. The question is, what does our central atom have? And in this particular case, the central atom also has an octet because it has 8 valence electrons, all found within single bonds. So this is the structure for difluoromethane. Let's look at SF2. We have 1 sulfur, we have 2 fluorines. Sulfur's in group 16, the last digit is 6, so it has 6 valence electrons. Fluorine is in group 17, the last digit is 7, so it has 7 valence electrons. The sulfur contributes 6, the fluorines contribute 14, so we have a total of 20 valence electrons to distribute. We need to develop the skeletal structure. In this particular case, the first element listed is going to be your central atom, around which you're going to place your other elements. We then are to draw a single bond between the terminal atom and the central atom and subtract 2 for each bond we drew. We drew 2 bonds. Each bond has 2 electrons, so that's a total of 4 electrons that are found in those bonds. And that gives us a total of 16 electrons still to distribute. The next step says to give your external atoms an octet. Our fluorine currently only has 2 valence electrons. In order to give that fluorine an octet, we're going to have to give it an additional 6 valence electrons. And that is true for both of our fluorines because they are identical. So in giving our fluorines their octet, we had to use 6 additional electrons. And so 2 fluorines at 6 additional electrons, that means we've distributed 12 electrons around our external or terminal atoms. That means we still have 4 valence electrons to distribute. Once your external atoms have an octet, if any electrons remain, they are placed on the central atom in pairs. And so we're going to place those 4 electrons on our sulfur atom in pairs. And we'll subtract out that 4, and we are left with 0. At this point, you say, does everybody have an octet? The fluorines have an octet because they have 8 valence electrons, 6 within the lone pairs, and 2 within the bond. That is true for both of our fluorine atoms. They both have 6 electrons in the lone pair and 2 within the single bond. Sulfur also is currently sitting with an octet because it has 4 within the bonds and 4 in the lone pairs, making a total of 8. This is the structure for sulfur difluoride. Now, the reason we know this is the structure for sulfur difluoride is because fluorine will always have a single bond. It will never have multiple bonds between sulfur and fluorine. Fluorine just can't. It just can't have more than one bond. Now, let's look at adding in a new piece of the puzzle. Let's look at adding in charge. In this case, we have 1 oxygen and 1 hydrogen. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons. Hydrogen is in group 1, the last digit is a 1, so it has 1 valence electron. The oxygen and hydrogen, therefore, are contributing 7 valence electrons to the overall structure. But you have to take into account the charge. This charge is saying add 1 to the total of valence electrons. So we're going to add 1 due to the charge to give us 8 valence electrons. The next step says to develop your skeletal structure. Well, when you have two atoms, the only possible skeletal structure is going to be linear. And therefore, we're going to put the two atoms together. Now we're going to distribute. The next step says to is to create a single bond between your external atom and your central atom. So in doing so, we've used up 2 electrons in our bond. That leaves us 6 valence electrons still to distribute. Our hydrogen currently has its octet because it has its duet, which is 2 valence electrons. Therefore, these electrons are going to go on the oxygen atom, and they're going to go on the oxygen atom in pairs. Once you've given oxygen its octet, you've used up the 6 valence electrons. And you have hit 0. Now that you've hit 0, you verified that everybody has an octet, and everybody does have an octet because your hydrogen has 8 valence, your hydrogen has 2 valence electrons, which is its duet, and oxygen has 8 valence electrons, which is an octet. It has 6 electrons in lone pairs and 2 in a bond. But we're not quite done. We've followed the rules that we have been following to date, but we have to add in the fact that this is an ion. And there are 2 factors that change. The first we've already done, which is take into account the charge when determining the valence electrons. The second is all ions must go in brackets with the charge outside the bracket. So our OH minus must be placed in brackets with the charge of a -1 outside the bracket. Let's look at another example. Let's look at H3O plus. We have 3 hydrogens and we have 1 oxygen. Hydrogen's in group 1, so it contributes 1 valence electron. Oxygen is in group 16, the last digit is 6, so it contributes 6 valence electrons. Between the hydrogen and the oxygen, we have a total of 9 valence electrons. But we have to take into account this charge. This charge is saying to subtract 1. So we subtract out 1 for the charge. And that leaves us 8 valence electrons to distribute. The next step says to develop your skeletal structure. Oxygen is going to have to be the central atom because hydrogens are always going to be terminal atoms. So we're going to take the oxygen and we're going to surround it by the 3 hydrogens. We then draw a single bond between the external atom and the central atom, and we subtract 2 for each bond we drew. We drew 3 bonds. 3 times 2 is 6, so we'll subtract out 6 valence electrons due to bonds. That leaves us 2 valence electrons remaining. When electrons remain, we make sure that every atom has every external atom has its octet. In this case, every single hydrogen has its duet, which is what it needs. It has its 2 valence electrons. So we don't need to distribute any more electrons to our outer atoms. Instead, we need to distribute the electrons on our central atom. So we're going to place those last 2 electrons on the central atom in pairs. And that gets us to 0. Now, when you hit 0, you verify, does everybody have an octet? Your hydrogens have their duet, and your oxygen does have an octet because it has 6 electrons within the bonds and 2 electrons in the lone pair. Now, the last thing we have to do is take into account the fact that this is an ion, and all Lewis structures for ions go in brackets with the charge outside. Okay, so thus far, all of our molecules have had an octet. But keep in mind, when you get to period 3, 4, 5, 6, and 7, the central atom can have an expanded octet, and that's perfectly okay. So let's look at the triiodide ion. You have 3 iodines. Each are in group 17, so the last digit is 7, so it has 7 valence electrons for a total of 21 valence electrons. We do have to take into account the charge. This is telling us to add 1 to our total valence electrons. That gives us 22 valence electrons we're going to need to distribute. Now, when all of the atoms are identical, such as in triiodide ion, it doesn't matter which iodine you put in, or which atom you put in as your central atom, and then you're going to surround it with the other 2. Now, you're going to draw a single bond between your external atom and your central atom, and you're going to subtract out 2 for each bond you drew. We drew 2 bonds. 2 times 2 is 4, so we'll subtract out 4 valence electrons due to our bonds. The next step says to give your external atoms an octet. Well, now, is this acceptable? Your current iodines, the outer iodines, have an octet because they have 8 valence electrons. But is it acceptable for the central atom to have 10 valence electrons? And in this particular case, it is, because iodine is in period 4 on the period, or period 5 on the periodic table. So yes, it is acceptable because that iodine can have an expanded octet. Now, lastly, this is an ion, so all ions must go in brackets with the charge outside. Now, let's look at nitrogen dioxide. And we're going to bring in yet another piece of information. Nitrogen dioxide. We have 1 nitrogen, we have 2 oxygens. Nitrogen is in group 15, the last digit of 5. Oxygen's in group 16, the last digit is 6. The nitrogen contributes 5, the oxygens contribute 12. Finally, we do, for a total of 17. We do have to take into account the charge. This is saying to add 1. So we're going to add 1 electron due to our charge. So therefore, we actually have 18 valence electrons to distribute throughout our molecule. The first element listed is typically going to be your central atom, around which you're going to place all other elements. You then draw a single bond between the central atom and the external atoms, and you subtract 2 for each bond you drew. We drew 2 bonds. 2 times 2 is 4, so we'll subtract out 4 electrons due to our bonds. which leaves us 14 electrons still to distribute. The next step says to give your external atoms an octet. We're going to do so by giving our oxygens an additional 6 electrons per oxygen in order for the oxygens to have an octet. The reason they needed 6 more electrons is because they already had 2 electrons in the bond. So 2 electrons in the bond and 6 electrons in the lone pair make a total of 8. So we have 8 valence electrons on our oxygens now, meaning they have an octet. In order to give our both oxygen atoms their octet, we had to use up 12 of the remaining electrons. And we still have 2 valence electrons to distribute. When you get to this point, if you still have electrons remaining, they go on the central atom in pairs. So we're going to place those electrons on the nitrogen in pairs. And we have hit 0. When you hit 0, you asked, does everybody have an octet? Our outer oxygens do have an octet. They have 8 valence electrons each. But our nitrogen currently only has 6 valence electrons. So no, not everybody has an octet. Now, everybody must have an octet except for hydrogen, which will have a duet. Everybody must have an octet except for hydrogen, which will have a duet. Therefore, we're going to have to bring in a pair of electrons to share between the outer atoms and the central atom. In the step that I just did, this structure emerges. And because we made an alteration, we go back to the question, does everybody have an octet? Your oxygen on the left still has 8 valence electrons because we did not alter that oxygen. The oxygen on the right has 8 valence electrons. It has 4 in the bonds and it has 4 in the lone pairs. And the central oxygen also has 8 valence electrons. It has 6 within bonds and 2 within lone pairs. Now to finish out this structure, we do have to put the ion in brackets with the charge outside. But here is the new piece. I made a conscientious decision that it would be the right-hand oxygen that shared its electrons in order to allow nitrogen to have an octet. There is no reason it had to be the right-hand oxygen when it could have been the left-hand oxygen and I would have had a similar result. Because of that fact, I can create what's called a resonance structure. And when you have a resonance structure, you must draw all forms of the resonance structure. And that resonance structure is going to be separated by a double-headed arrow. So this is the structure for nitrogen dioxide, or nitrite. Now, we just looked at the nitrite ion. Note that it had a negative charge showing. This is different. This is nitrogen dioxide, and it does not have a negative charge showing. So we're going to do things, but it's going to be different. We're going to do similar things, but there are going to be some differences, is what I meant to say. We're going to start with the fact that there's 1 nitrogen and 2 oxygens. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. The nitrogen contributes 5, the oxygen's 12, for a total of 17 valence electrons. We're going to determine the skeletal structure. Nitrogen is going to be our central atom around which we're going to place our oxygens. We're going to draw one bond for each, between each external atom and the central atom, and subtract out 2 for each bond we drew. We drew 2 bonds. 2 times 2 is 4, so we'll subtract out 4 electrons due to the bonds. That means we have 13 valence electrons still remaining. The next step says to give your external atoms an octet. So we start by giving our oxygens their octet. In order to give each oxygen an octet, it needs 6 additional electrons to complement the 2 electrons that are found in the bond. 6 electrons on each oxygen, 2 times 2 oxygens means that we've used up 12 electrons due to our outer atoms, and we have 1 valence electron still remaining. Now, any electrons that are still remaining, they're placed on the central atom in pairs unless you have a lone electron, in which case you can only place 1 because you can't place more electrons in the bond or in the molecule, excuse me. You cannot place more than 1. You cannot place more electrons in the molecule than you have valence electrons. And we have hit 0. When you hit 0, you asked, does everybody have an octet? Our outer oxygens both have 8 valence electrons because of the fact that they have 6 in the lone pairs and 2 in the single bond. Our nitrogen currently only has 5 valence electrons because it has 2 in the single bonds each for a total of 4, and it has 1 free radical. Now, because nitrogen does not have an octet, we're going to share a pair of electrons between an outer atom and the central atom. And this structure emerges. And you asked, does everybody have an octet? Because we didn't alter the left-hand oxygen, it still has 8 valence electrons. What we really need to do is look at what happened to our other oxygen and then the nitrogen. Our other oxygen still has 8 valence electrons. It has 4 within the lone pairs and 4 within the double bond. Our central nitrogen has 7 valence electrons now because it has 6 within the bonds and 1 free radical. Now, it is tempting to say, okay, not everybody has an octet, so I'm going to share another pair of electrons, and because chemistry likes symmetry, I'm going to share it from the left-hand side. And we go through this process, and we would see, okay, this is the structure that emerged, and our oxygens still have their octet because they still have 8 valence electrons. And now our nitrogen has an octet, a minimum of an octet, because it has 9 valence electrons. However, this structure cannot exist. Period 2 elements cannot have an expanded octet. Because d orbitals do not exist. Only once we get to period 3 elements and beyond can we have an expanded octet, because only once you get to N equals 3, do you have the availability of the D subshell? So our structure is once again a resonance structure. We created this structure in the last valid step. But again, this structure, I made a conscientious decision that it would be the right-hand oxygen that shared the electrons. And I could have made an equal decision by making it the left-hand oxygen. Therefore, I have created a resonance structure where I illustrate that fact by using a double-headed arrow and then drawing the other resonance structure. So this is the Lewis structure for nitrogen dioxide. If you have a resonance structure, you must show the resonance structure, folks. Otherwise, it's incorrect. Now let's look at another example that combines many of the things that we have talked about. Let's look at the chlorate ion. We have one chlorine. We have 3 oxygens. Chlorine is in group 17. The last digit is 7, so it has 7 valence electrons. Oxygen is in group 16. The last digit is 6, so it has 6 valence electrons. The chlorine contributes 7. The oxygens contribute 18, so we have 25 valence electrons to distribute, but we must take into account the charge. This is telling us to add 1. So we're going to add 1 due to the charge. So we actually have 26 valence electrons that we need to distribute. The first element listed is typically your central atom, and you're going to surround it with the other elements. You then draw a single bond between the terminal atoms and the central atom, and you subtract 2 for each bond you drew. We drew 3 bonds. 3 times 2 is 6, so we'll subtract out 6 electrons due to bonds. And that gives us 20 valence electrons still to distribute. The next step says to give your external atoms an octet. Oxygen currently only has 2 electrons found within the bond. So in order for our oxygen to have an octet, we need to give it 6 additional electrons. This is going to be true for all 3 of the terminal oxygen atoms. So by the time we have given all of our terminal oxygen atoms their octet, we've used an additional 18 electrons on the outer atoms. And that leaves us 2 valence electrons still to distribute. The next step says that if electrons remain, they go on the central atom in pairs. And so we're going to place those last 2 electrons on the central atom in pairs. And we have hit 0. Once you hit 0, you always ask, does everybody have an octet? Your oxygens all have 8 valence electrons. And your chlorine has 8 valence electrons. So yes, everybody has an octet. However, chlorine is in period 3. Since it's in period 3, it can have an expanded octet because it has the availability of the D subshell. To determine whether you need to expand this octet, you must calculate the formal charge of every element. So we are going to do the formal charge of our single bonded oxygen. They all look the same, so right now I'm going to treat them all the same. This formal charge is equal to the number of valence electrons, which is 6, minus 1 for every electron owned by that element. So that means that it owns 6 plus 1 for every bond. So it's, in other words, 1 for every dot and 1 for every bond. So the formal charge on all of these oxygens is a -1. Let's look at the formal charge on our chlorine. Chlorine is in group 17, so it has 7 valence electrons, -1 for every dot. It has 2 dots, +1 for every bond. It has 3 bonds. So right now, this is sitting with a +2 formal charge. This molecule has an overall charge of 5 right now because it has 2 in the chlorine and 1 in each of the oxygens. That's a lot of formal charge. So in other words, we're going to have to minimize this formal charge. So let's bring in a pair of electrons to minimize the formal charge. And let's see what happens when we do so. So we have our oxygen and our chlorine and our second oxygen. All of this is still the same. And then we have a double bonded oxygen. That is our only change that we made. We checked, does everybody have an octet? And if you do so, you're going to see, yeah, everybody has an octet. And right now, chlorine even has 10. But does chlorine need a further expansion of its octet? Does it need to expand its octet further? So we're going to do the formal charge. The formal charge of our single bonded oxygens is going to be equal to 6 valence electrons -1 for every dot. They have 6 dots and 1 for every bond. It has 1 bond. So again, they still have a formal charge of a -1. Our double bonded oxygen has 6 valence electrons -1 for every dot. It has 4 dots +1 for every bond. It has 2, so it now has a formal charge of 0. Our chlorine, it is 7 valence electrons -1 for every dot. There are 2 dots +1 for every bond. It now has 4 bonds, so it now has a +1 formal charge. So we went from a total of 5 formal charge to a total of 3 formal charge. That is much better. However, we can reduce it further. And one of the tricks you'll notice is I'm always taking electrons from somebody that has a formal charge of -1, and I'm dropping it between the elements that have the -1 and the +1. So once we get this structure, this is what emerges. And if you calculate the formal charge, you will see that we have a formal charge of a -1 on the oxygen that's single bonded. We have a formal charge equal to 0 on both of the oxygens that are double bonded. And now we have a formal charge equal to 0 on the chlorine as well. So we have minimized the formal charge. We got it as close to 0 as possible. It's not going to be 0 because we have a charged ion. So it's not going to be ever equal to 0. It has to equal the charge on the ion. Now, this is an ion, so it is needed to be placed in brackets with the charge outside. The other thing that I will say about this is, why did it have to be the right-hand oxygen and the top oxygen? Why not sharing of electrons in another way? The fact is we could have shared electrons in a different way. And therefore, what we need are resonance structures. And this structure is going to have 3 resonance structures. And you must be prepared to draw all the resonance structures. In order to get the problem right. So this would be the Lewis structure for the chlorate ion. Let's look at another example. Let's look at sulfur hexachloride. You have 1 sulfur, you have 6 chlorines. Sulfur is in group 6, the last digit is 6, so it has 6 valence electrons. Chlorine is in group 17, the last digit is 7, so it has 7 valence electrons. The sulfur contributes 6, the chlorines contribute 42, for a total of 48 valence electrons that are going to need to be distributed. The central atom is going to be sulfur, around which we're going to place all of our chlorines. And we're going to draw a single bond between the sulfur and the chlorines. We subtract out 2 for each bond we drew. We drew 6 bonds. 6 times 2 is 12, so we'll subtract out 12 due to our bonds, leaving us 36 still to distribute. The next step says to give your external atoms an octet. Chlorine currently only has 2 valence electrons within the bond, so we have to add an additional 6 valence electrons to each chlorine in order for the chlorines to achieve an octet. Six valence electrons times 6 chlorine atoms means that we used up 36 valence electrons on our outer atoms. And we have hit 0. When you hit 0, you ask, does everybody have an octet? Our chlorines have an octet because we just gave them an octet. And our sulfur currently has 12 valence electrons. But that's okay because sulfur can have an expanded octet because sulfur is in period 3. It can have an expanded octet. So this is the structure for sulfur hexachloride. It will be sulfur that is single bonded to 6 chlorides. Let's look at one more example. Let's look at the sulfate ion. Sulfate, we have 1 sulfur and 4 oxygens. Sulfur is in group 16, the last digit is 6, so it has 6 valence electrons. Oxygen is in group 16, the last digit is 6, so it contributes a total of 24 valence electrons for 30 electrons to be distributed. But we have to take into account the charge, and this is telling us to add 2. So we're going to add 2 valence electrons due to our charge, for a total of 32 electrons that need to be distributed around the molecule. The central atom is going to be sulfur, around which we're going to place the 4 oxygen atoms. We're going to draw a single bond between each of the sulfur and the oxygens, and we'll subtract out 2 for each bond we drew. We drew 4 bonds. 4 times 2 is 8, so we'll subtract out 8 due to bonds, leaving us 24 still to distribute. The next step says to give your external atoms an octet. The oxygen currently only has 2 valence electrons found within its in the single bond to sulfur. So in order for our oxygens to have an octet, we have to give each oxygen atom an additional 6 valence electrons. 6 times 4 is 24, so we used up all of our valence electrons on our outer atoms. When you hit 0, you ask, does everybody have an octet? In this particular case, we would find out, yes, everybody has an octet. However, sulfur is in period 3. Period 3, 4, 5, 6, 7 elements can have an expanded octet because they have the availability of the D subshell. Because they can have an expanded octet, we have got to check the formal charge to see if we need to expand the octet. The formal charge for the oxygens is that it's going to be 6 valence electrons minus 1 for every lone electron. So that would be 6 plus 1 for every bond. So that's 1, meaning that the formal charge on those oxygens are minus 1. Now let's do it for the sulfur. The formal charge on the sulfur. Sulfur has 6 valence electrons minus 1 for every dot. It had 0 dots, and 1 for every bond. It had 4 bonds. So that leaves that sulfur with a plus 2 formal charge. The sulfate ion, the way it is currently designed, has 6 overall formal charge. That's bad. So we need to minimize the formal charge, and we're going to do so by making a multiple bond. So when we bring in a pair of electrons to make a multiple bond, this structure emerges. Now, because we altered the structure, we do need to check formal charge. One thing you will note is if you do the formal charge of the single bonded oxygen, it's still going to come out to be 6 valence electrons minus 1 for every bond, which is, or 1 for every dot, which is 6, plus 1 for every bond, which is 1, meaning it's a minus 1. So one thing you'll notice is that if you don't alter the element, you're not going to alter its formal charge either. So all of these single bonded oxygens still are going to have the -1 formal charge. So what we really should be checking is what happened when we altered the structure. So what happened to the double bond? Well, or when we made a double bond? Well, that's going to be equal to 6 valence electrons minus 1 for every dot. There are 4 dots plus 1 for every bond. There are 2. So it's now got a formal charge of 0. So this has a formal charge equal to 0. The other thing that underwent a change is going to be the sulfur atom. It has 6 valence electrons minus 1 for every dot. It had 0 dots plus 1 for every bond. It now has 5. So that means it has a plus 1 formal charge. So what we did is we went from 6 to 4. So we definitely improved it, But again, can we improve it further? And the answer is yes, we can make another double bond by bringing in a pair of alone electrons. And when we bring in those electrons, this structure emerges. And why did I bring it in from the bottom? Because chemistry likes symmetry. Now, again, you know the formal charge of these that have not undergone a change since the last one. They are still going to be the same. The question is, what happened to the formal charge of what underwent a change? So the formal charge on the oxygen that underwent a change is now 6 minus the number of dots, which is 4, plus the number of bonds, which is 2. So that means it has a formal charge of 0. And our sulfur also underwent a change. So that was 6 valence electrons minus 1 for every dot. It had 0, 1 for every bond. It has 6 bonds, so it has a formal charge of 0 too. So we have minimized it down to 2. We're not going to get any further because you will notice that the sum of the formal charges in our molecule is equal to the sum of the charge on the ion. So you're not going to get it any further than that. So in order to finish this, this is an ion. So the ion needs to be placed in brackets with the charge as a superscript. But here again, why does it have to be the north and south oxygen? Why couldn't it have been the east and west? And the answer is, well, it could have been. So therefore, I have a resonance structure. In the lab, you're going to get practice developing the Lewis structures this week. And therefore, you're going to get to see all of these rules in action, and hopefully start to memorize them because you're practicing them enough. So I expect lots and lots of questions during lab.